All right, we're going to look at 10.1 chi-square test of independence. So we're going to do some more hypothesis testing, and we're going to use a different distribution to test this hypothesis. All right, so we're going to use this chi-square graph, and just like with the student's t-graph, there's a collection of them, and that collection is is affected by the degrees of freedom. And just like with the student's t distribution, the more degrees of freedom you have, the better this approximates a normal distribution. So you can see with only 1 degree of freedom, doesn't look normal at all. With 5, it's starting to start to look like that normal distribution. With 10, it's even more. And so as we get more and more, it's going to be a better approximation for that normal distribution. But this is what we're going to use, this chi-square. So I put on there for 4 different graphs and charts for you to use. We've used 2 of them were the Z tables, and then we had the student T table, and then this is the 4th one. So you'll need a copy of this as you do these problems. So make sure if you don't have it yet, go ahead, stop the video, go get a copy of it, print off a copy, and then come back to it. And it should look, kind of like that. And you can kind of see how, it's starting to become normal there. So we're going to look at that. It's kind of, the reading is kind of similar to how we read the student's t-chart, with the degrees of freedom on one axis and the area on the other. The table is going to be based on the right area on the right tail. Okay, so if we're doing luckily we're only doing, we're going to be doing 2-tailed tests, but based on this area, we're just going to use this one value from it. So we're not going to double it. And you're going to notice this distribution is skewed to the right, All right, so we're going to do some hypothesis testing. We're going to test to see if 2 value variables are independent. And our null hypothesis is always going to be that they are independent, and our alternative is that they're not independent. We're also going to test to see if the proportions or probability of success, that type of thing, if 2 populations have the same proportions, again, our null hypothesis is always going to be that they have the same, and then the alternative is going to be not have the same. And then we're going to use the same measure way we decided whether to reject or not. If it's less than or equal to this level of significance we're given, we're going to reject. If it's greater than that, we're not going to reject. And again, that's going to be we're going to compare, the p-value is going to be the area under that curve to the right, Okay, so let's look at number 14 on page 263. Give me a second. Okay, sorry, 636. I don't know what I said before. Number 14 there. All right, so the following table shows the Myers-Briggs personality preferences, an area of study for a random sample of 519 college students. Let's see. In the table, IN refers to introvert intuitive, EN extrovert intuitive, IS introvert sensing, and ES introvert extrovert sensing. So those are, there's 2 more ways of defining things on the Myers-Briggs. We're not going to worry about that for this. We're going to use a chi-square test to determine if the Myers-Briggs preference is independent of the area of study at the 5% level of significance. So these are our 2 variables, your preference there, and then whether someone went into arts and science, whether they went into business, or when they went into allied health. And they have this data here, and we're going to try to see, is it independent? Does it, could someone with a intuitive introvert be just as likely to go into business as somebody with an extrovert sensing preference? So let's see how we're going to do that. All right, so the first thing we're going to do is we're going to find the expected value for each cell. And the expected value, the way you're going to calculate that, row total. So you're going to go across the row, see the row total here. And for some reason, there it goes, row total. And then you're going to multiply that by the column total. So you're going to cross-reference. So to find this first spot, I would take 96 times 289, and I would divide that by the sample size. And the sample size is this 519. And so for that first value, I would get, this is the expected value if they were independent. This is what I would expect to get. So 52, basically about 52.5. 52.5 approximately. That's what I would get for that spot. And we got 64. So 64 is the observed value. This is the predicted or the expected value if it was independent. Now, of course, you might say, well, they're not the same. So that proves it. All done, finished. No, that doesn't prove it. Obviously, in an ideal situation, that would be evidence. But there's always going to be some variance. Because I mean, this is just a sample. We don't have 100% of all students and their majors all over, every society in the world. So we can't really make that claim yet. They're not the same. The question is, are they so far off that it could only happen if these are not independent? And that's what we're going to figure out. Now, before I move on, I just want to kind of explain where this expected value is coming from. So if I wanted to know what's the probability that a student was IN, introverted, intuitive, then what I would take is 96 over 519. That's the probability someone would end up in the IN row. And if I wanted to say, what's the probability that a student majored in arts and science? Well, I would take 289 divided by 519. Okay. So again, that's the column, how many people are in the column divided by 519. And then if I said, what's the probability that a student is IN and arts and science? Okay, so I would multiply these two together, 96 times 519, or 96 over 519 times 289 over 519. Okay, and you might say, well, okay, I can see where the 96 is coming from. I can see where the 289 is coming from. But on the bottom, I only have one 519. Why is that? Well, remember, this is the probability you would end up there, but the expected value would be the sample size times that probability. So it would be whatever that is times a 519, right? So it'd be all this in there. Well, that would cancel out one of the 519s. And so that's why it comes out to be this formula. So that's what's going on there, where that formula. So if you're like, how did they calculate that? That's what it's doing. Okay, so but you just do that for each cell. We'll just do that for each cell, do that calculation. So row total, column total, divide by the sample size. All right, so this first one, our expected value we said was 52.5. So I would take, to go IN business, I would take 96 times 134 and divide that by 519. And that would be about, and I'm just going to go one decimal place on all of these, 24.8. And then what would be my expected value for allied health with IN? 96 times 96 divided by 519. So 17.8. So, that's pretty good. That's pretty close. That's why I said you can't just go by, oh, they're different. They're different, but are they way different or just kind of different? And so we're just going to go through and multiply the row total by the column total, divide by the entire size of the sample, 519. for each one of these, cross-reference those. So I'm taking 154 times 289 divided by 519 to get the EN Arts and Science. And that gave me 85.8 about. And so I'm just going to go through and do all of those. 154 times 134 divided by 519. 39.8. 154 times 96 divided by 519. 28.5. We got 115 times 289 divided by 519. About 64.0. 115 times 134 divided by 19. That's a 29.7. 115 times 96 divided by 519. 21.3. Okay, 289 times 154 divided by 519. 85.8. $39.8 and 154 times 96 divided by 519 and 28.5. 28.5. So those are all the expected values. So that's the first step. Calculate all those expected values. All right. So now that we have what we are observing, what they actually got when they did the study, and we got what we would expect to get if these were independent, now we're going to do our testing. Now we're going to see, all right. And, just a reminder, what are we testing? That we're testing variables are independent. And the alternative is the variables are not independent. Now, notice we're not testing to see if they are, I want to say it, causational. They're that one of them is causing the other. We're just looking for, maybe there's a correlation, some kind of inverse correlation or direct correlation or whatever, but that they're not independent. They're not acting just, one's doing one thing and the other one's doing the other, and they don't really affect each other, that there is some connection between the two. So that's why you'll notice the second one is that they're not independent, but we're not really saying, they both might be affected by something else. And we're not exactly sure, but they're not independent of each other. There's some relationship there. All right. So, let me get these values. I have these values written down. So let me get those values in there. Yep. Okay. And let's see, let me just check the first column. 53 point. Is that a typo? 58.64 looks good. 85.8. Let me check that first one. Did I do that wrong? I mistype it. 96.289 divided by the other ones all look right. So, no, I wrote it down wrong. I read my calculator. This is a 3. This is a 3. Always check yourself. When in doubt, always check yourself. All right. So yeah, I mistyped it from my calculator. 24.8, 39 point. Make sure I got all these other numbers written down correctly. 17.8, 28.5, 21. Okay. All right. So I'm going to fill in those other numbers here. 24.8, 17.8, 39.8. You'll notice I'm leaving some room underneath there because we're going to do some more calculations here. 29.7, 21.3, 39.8, and 28.5. So, you might want to draw yourself a table and for these other things we're going to calculate. Okay. So here comes the second step. Second step is to calculate, sorry, the chi-squared test statistic. And what that is the sum of the difference between your expected minus, or sorry, your observed minus your expected squared divided by your expected value. So for this first block, what I would do is I would take my observed 64 minus 53.5, square that, and then divide it by the expected, which is 53.5. And that's, I'm just going to write that value in the square under these other two. Because what we're going to need to do is then add them all up. So we have to calculate them all first, and then we'll add them all up. So 64 minus 53.5, close that up, squared, divide by 53.5. And I'm going to go 2 decimal places on this. I think, yeah. So 2.06. 2.06. So I'm just going to do that for all of these. I'm going to take the observed 15 minus the expected 24.8, close that up, square it, divide by the observed 20, or the expected 24.8, and we're going to get 3.87. So notice if this was a perfect match for the expected, each of these would be 0, right? You'd have the same number for the observed minus the expected, and then you'd get 0, and then you square it and divide, and you'd still get 0. So the larger this value is, the more different the observed and the expected are from each other relative to the size of the expected value. So 17, whoops, don't forget the parenthesis, 17 minus 17.8 squared, divide by 17.8. And make sure you're dividing by the expected value, not the observed. That's going to give you a different number. Okay, so that's about 0.04. So 82 minus 85.8 squared, divide by 85.8. Okay, so that's about 0.17. Okay, so again, those two kind of close. 42 minus 39.8 squared, divide by 39.8. So 0.12. So some of these aren't huge differences. .08 looks like. All right. 68 minus 64, square that difference, divide by 64. 0.25. 35 minus 29.7. Oops. Divided by 29.7. 0.95. 12 minus 21.3 squared. This is probably going to be kind of big, relatively speaking. Yeah, 4.06. All right. 75 minus 85.8 squared, divided by 85.8. 1.36. 42 minus 39.8 squared. Okay. Almost got confused because the two E's for that are the same, but okay, numbers are the same, so that happens. 37 minus 28.5 squared divided by 28.5. So this is 2.54. All right, so we need to add all those up. This is the sum of all those. So we're going to add all those up. 2.06 plus 3.87 plus 0.04 plus 0.17 plus 0.12 plus 0.08 plus 0.25 plus 0.95 plus 4.06 plus 1.36 plus 0.12 plus 2.54. And I got a chi-squared value of 15.62. Okay, so, but we also need, figured I wrote on top of it, degrees of freedom. And the degrees of freedom are the number of rows minus 1 times the number of columns minus 1. Now, when it says rows and columns, it's not of the chart, it's of the data. So we have 1 column, 2 columns, 3 columns, and we have 1 row, 2 rows, 3 rows, 4 rows. So it's not of the chart, it's of the actual data inside. So this would be, for my degrees of freedom, this would be R minus 1, rows minus 1, so 3, columns minus 1, so 2, so 6 degrees of freedom. So I have this chi-squared, kind of hard to see now that kind of pop that on top of each other, but chi-squared and degrees of freedom, and I'm going to use that to go to the table. So let me pull the table up real fast. So I'm going to pause this for a second and grab the table. Okay, so let me, we got that chi-squared 15.62, degrees of freedom of 6. So I'm going to go here. This is the table. So let me write that down somewhere. Chi-squared 15.62, degrees of freedom, we calculated to be 6. So here's my degrees of freedom. And what I'm going to do is I'm going to go across here until I figure out where that 15.62 should be falling. And it should be between these two values. So up here, this is going to give me an interval for my p-value. So my p-value is between, p-value is between, I'm messing this up, between 1%, not 10%, 1% and 2.5%. 1% and 2.5%. Messed myself up by putting that extra 0 in front of the decimal. All right, 1% and 2.5%. So this set it for us to use an alpha value 0.05. So this is less than, the p-value is less than or equal to our alpha value. So we should reject the null hypothesis. We should reject the idea that the personality preference and the area people would major in are independent, that there is some kind of relationship there between those. And so you could think of, if you were a counselor, a high school counselor, you might have a student take a personality assessment, kind of figure out where they are on that personality assessment, and then, make some suggestions. Like, it seems like people with your personality type like this kind of area, they tend to major in this kind of area. Now that should never be used as a strict, like you have to do it. That's not what that, if somebody's using it as that no, because as we can see, there's people in all the different areas. It just happens to be that some people tend, certain personalities may tend towards one area over another. And, this data doesn't really give that. I mean, you could kind of eyeball it and see, but, most people are in the arts and science, no matter what area they are. It just happens to be that if you're I would probably compare it left to right versus up to down or something, but you can kind of say, well, there is some kind of relationship there, and that, with more studies, we could make better predictions as to what might be a good fit for someone. And they do that. They do testing sometimes to see what job career might be a good fit for someone based on that, on their personality type. But no one is locked in. Obviously, you can have a personality type and do any kind of job. It just, some people may be more naturally leaning that direction, is what this is indicating. Okay, so for the homework, we're going to do 1 through 3 all, and then 9 through 13 odd. And you're going to be, like I said, I would make a table and make sure you have room to put the observed value, the expected value, and then the value you're going to use for your chi-square calculation. And so you can just have all that information in a nice organized fashion to figure it out. And we're going to see if are these things independent or not independent. That's the hypothesis you're going to be looking at. Null hypothesis, they're independent. Alternative, not independent. Those are the two things. So whatever we're looking at. All right. So have a good day.